make things punctual. So let us start this second plenary conference. And it's a great pleasure for me to introduce Professor Samson Abramsky. I'll not give all the details, but for plenary conference, it's important to give some of the details of who we are talking with. And he has spent part of his career in many of the important United Kingdom institutions nowadays, and he does not take part in those things, so he took degrees from Cambridge, degrees from Oxford, and everything in different institutions. And nowadays he's a professor at Oxford. And I'll just list that he was the Clifford Lecturer at Tulane University for 2008. It's a very distinguishable thing. He has a BCS Lovelace Medal from 2013. And also, last year, he got the Alonzo Church Award for Outstanding Contribution to Logic and Computation. And one of the prizes that I really admire more, and that I think that our society could think about something in similar terms, is the Test of Time prize. That's something that you wait 20 years to say, okay, in those list of contributions of 20 years ago, this one was really something very important. And he received this Test of Time award in 2007 from a paper from 1987, that is related to the domain theory in logical form. And he was prepared to talk about semantics and many interesting aspects of logic, but we essentially concluded that it would be better for change topics and to talk about contextuality. That's something that he started working some 5 years ago or a little bit more. And nowadays he's one of the active members of this community. So please welcome and enjoy Professor Samson Abramsky. And let me tell another point. Who is disappointed with, oh no, I will lose the talk about semantics. He will be here up to Saturday. And he's a very easy speaking guy. Never mind about the prizes. He deserves all of them, but there is no barrier in approaching him and discuss whatever you want. Okay? So please, Professor.
Thank you very much. It's a great pleasure to be here and have the opportunity to speak at this meeting. So my thanks to the organizers and especially to Marcelo for inviting me and hosting my visit. It's great to be here. So indeed, I've changed topic, but in a sense we're not so far from logic, although we're also dealing with quantum mechanics and physics, because we'll be speaking about quantum contextuality at the borders of paradox. And I thought this might be a nice and appropriate topic also to speak about here, because there's a great tradition in Brazil of the study of paraconsistent logics. And actually in Campinas, Newton da Costa and Walter Carnielli and others have done major work in that topic. So we won't exactly be speaking about paraconsistency, but paradox will be a central theme of this talk. So I thought I'd begin with the first. So I've been in computer science, and very early on in my career as a graduate student in computer science, doing a PhD, I learned an axiom. We don't often speak about axioms of computer science, but I heard this axiom from my PhD advisor only a few weeks after I started. I hope you can read this green color. It says, computers might as well be made of green cheese. So there's, of course, the idea that the moon is fancifully made of green cheese. And the point was, behind this, that what we'd learned in computer science is to work at a certain level of abstraction. Yes, computers are made of semiconductors or integrated circuits, I mean all the things that we've developed in computer hardware, but we abstract away from these physical realities and we just focus on a kind of mathematical model of machine, whether it's Turing machine circuits or some kind of high-level programming language. And for many purposes, this is a very sound policy to work at these higher levels of abstraction. But one of the interesting things that's happened over the last 20 years is that in some sense this axiom has been refuted. It's no longer safe to assume this. And of course, one of the main, or the main reason for this is the rise of quantum computing, where it's now in principle possible to, and we anticipate a revolution in the practice of computing by taking advantage of the new possibilities opened up to us by the fact that our world is ultimately described not by classical physics but by quantum physics. So, and the interesting thing is that current work in quantum information and computation is really using mathematical tools developed in the mathematical foundations of computation, and it delivers exciting new challenges and possibilities for computer science. And of course, when we look at quantum computing, we're interested in the new things we can do using explicitly quantum features, which we can't do using just classical computers. And there, what we see is that these new possibilities for quantum advantage sit at the very boundaries of paradox in a way reminiscent of something that we already know in classical computing, where recursion, programs that, subroutines that call themselves in an obviously circular fashion, are actually one of the fundamental tools of programming, and their mathematical foundations are really based on the so-called paradoxical combinators and fixed points, which were developed by logicians studying the foundations of mathematics. So, so I don't know how many of you have encountered the Y Combinator. If you type in Y Combinator and you go to Wikipedia, you find a disambiguation. So, and this is very telling, because the two possible meanings are, firstly, the Y Combinator, a very abstract mathematical object discovered by by Haskell Curry and by the people by Church, Alonzo Church, in studying the foundations of mathematics through the lambda calculus. And on the other hand, it's a company, a startup company accelerator, and actually quite a giant in that field in Silicon Valley. So the Y Combinator company has been called a spawning ground for emerging tech giants. So, and a lot of very well-known companies have sort of grown up through the incubation process with Y Combinator. And it was actually started by Paul Graham and his colleagues, who were Lisp gurus, who made very effective use of Lisp in developing their own software in the early days of web interface software. And Lisp itself is directly based on the lambda calculus. And the Y Combinator was introduced by Haskell Curry, and what he was doing was studying Russell's paradox, one of the fundamental logical paradoxes. So here we have this remarkably, so we don't need to go into the details of this, but it's a wonderful thing. If you've never played with the untyped lambda calculus, you can do amazing things with it. The point is there's this remarkably direct connection between something at the absolute foundations of mathematics. I mean, Russell's paradox created the crisis in the foundations, one of the main things that created the crisis in foundations at the beginning of the 20th century, to, on the other hand, things that are absolutely current in modern software technology. And this very direct link is one of the fascinating features of these developments. So the Haskell functional programming language that some of you may have encountered is named after Haskell Curry, in fact. And we may have encountered these things for example, in Douglas Hofstadter's classic book Gödel, Escher, Bach, or you may have encountered the paintings by Moritz Escher, the drawings by Moritz Escher, which evoke in a wonderful visual way this idea of circularity as the two hands drawing each other, for example. And in some sense, these are direct reflections of exactly these kinds of ideas. So what we see is that paradox is not just something that is sort of negative and destructive, it can lead to very creative developments, even in classical computing. And in some sense, as we'll now see, when we go on to quantum mechanics, it goes a step further, and the whole interest of quantum mechanics is very much concentrated in these phenomena that lie close to the borders of paradox. So we are witnessing now the beginnings of quantum technologies for information processing, things like quantum key distribution and other security protocols already significantly deployed. There's significant investment in so-called post-quantum crypto, how you strengthen crypto systems on the assumption that the bad guy, the adversary, may have a quantum computer, randomness certification and amplification, and things on the horizon, simulation of quantum chemistry, quantum machine learning, and optimization. And major companies such as Google, Microsoft, IBM, Amazon too now are getting involved in these developments in a major way. And the point we want to make here again is that these remarkable developments are directly connected with ideas from quantum foundations. So the study of quantum information and quantum computation has really revived interest in quantum foundations. And these quantum foundations ideas are closely associated with a number of paradoxes or quasi-paradoxes, such as Bell's theorem, the Cauchy-Specker paradox, Hardy's paradox, teleport. So the very names tell you that something strange is going on. Some of these things are called paradoxes. Teleportation makes us think of Star Trek, pseudo-telepathy, and then these phenomena underlying all these things of non-locality and contextuality. So what all this suggests, and what we'll try and confirm, is that the borders of paradox are a fruitful place to be. Perhaps we don't want to cross those borders, but just as people speak of the edge of chaos as being a fruitful place to be, so perhaps the borders of paradox are a fruitful place to be. So if we think about the borders of paradox, usually we regard logical consistency as a minimal requirement for scientific theories, or indeed for rational thought in general. But if we want to make sense of contextuality and the allied phenomena, then we need to take a richer view of consistency. This phenomenon of contextuality is manifested in these classic no-go theorems. So as a matter of interest, how many people in the audience, could you raise your hand if you've heard of Bell's theorem? Not so many. Well, by the end of this lecture, everyone will have heard of Bell's theorem and actually will have seen a proof of it and will be able to prove it yourselves, because it's... So these things are manifest this phenomenon, and the very fact that terms such as paradox, that these are referred to as paradoxes, illustrates the close relation of these results to issues of consistency. At the same time, what we should emphasize, and we'll say a bit more about this later, is that these arguments are empirically grounded and have been, in a considerable extent, experimentally tested. Moreover, and this is an emerging theme, which, for example, is well illustrated in the special session on mathematics of quantum theory, which is ongoing in the conference here. We just had an excellent first part of that. It can be argued that contextuality can be seen as an essential resource for quantum advantage in computation. So somehow the idea of using quantum systems to do things that classical systems can't, it can be in large part leveraged on this connection with this situation of being at the borders of paradox. Okay, so I mentioned the word contextuality several times, but what is it? So I think, to my mind, my favorite slogan for contextuality, and what I think gives the right intuition, is that it arises where we have a family of data which is locally consistent but globally inconsistent. So what do we mean by this? Well, again, we can illustrate it very well with, in a visual way. So suppose we're looking at some building from afar. We have a camera with a limited aperture, so we can take pictures of parts of the building. And if you look at each of these parts, the snapshots of each of these parts, they look perfectly reasonable in themselves. So I think you'll agree. And even if you look at the adjacent borders, they fit with each other in a consistent fashion. So we can think of this as a family of data which is locally consistent. But now, of course, we assume that these are pictures of a single real building, so we should be able to put all the pieces together. And if we do that, we get this also. I don't know how many of you have seen this before. This is a famous drawing by Escher, the so-called ever-ascending staircase. And you see that it's actually, if we think of it as a real staircase in three-dimensional physical space, it's paradoxical, because we somehow, depending on which way you look at it, we're either always going upwards or always going downwards. So there's a problem with global consistency. Now, this, of course, is a visual paradox, and we might think no more of it than that, but we'll see this kind of structure deeply reflected in our best physical theory. So to go towards seeing that, let's think of the following experimental situation or empirical situation. We have two agents, Alice and Bob, and we imagine them situated maybe at 2 points in some network. Alice has two local registers, bit registers, and a processing unit where she can load a register and inspect the content. So Alice can either load A1 and see if it's 0 or 1, or she can load A2 and see if it's 0 or 1. Bob similarly can load either B1 or B2. And in some round of sort of observation, each of them chooses one register, loads it, inspects the contents, and sends the answer to some target node where the answer is recorded. There's incidentally another way of looking at this as a kind of game. Perhaps I'll omit that here, but we'll think of it as an experiment. Now, what we can imagine is that we perform multiple rounds of this experiment, where on each round Alice chooses a register, inspects it, sends the contents, Bob chooses a register similarly, and then we can look at frequencies in which different answers arise depending on which of the registers have been inspected. So we might get a table that looks like this. I mean, if things settle down and we get nice limiting frequencies, so we get probability distributions. So for example, what this table says, or the entry in row 2 and column 3 that's highlighted says, in those cases where Alice looks at register A1 and Bob looks at register B2, then 1/8 of the time Alice sees a 0 and Bob sees a 1. Okay, and all the other entries have similar interpretations. And you see that for each row, which represents all the possible outcomes for some given choice of registers, we get some non-negative numbers summing to 1. So it's a probability distribution. So this sort of makes sense. The question is, how could we explain this behavior? What kind of mechanism could we invoke to explain this behavior? So the natural thing we could imagine is that there is some generating process which we'll speak of as a classical source. And what this does is because of course Alice could choose to look at either A1 or A2, and there's always something in the register when Alice looks at it. So on each round we could imagine some process which chooses values to write in all of these 4 registers, A1, A2, B1, B2, and how it chooses which values to write may itself be probabilistic. So the source may flip a coin or several coins and decide which value to put in each of the 4 registers. Then Alice looks at one of those registers and, of course, finds the value that the source has put there. So in this case, the source has written 0 into A1, 1 into A2. So Alice chooses to look at A2, and that's the value 1 that she gets, and similarly for Bob. So the question is, and that's a perfectly reasonable classical mechanism. There's nothing disturbing there. Is that sufficient to explain this observed behavior? And here's the wonderful thing. We can conclude by a simple argument that, in fact, no such classical source can explain that table of behavior that we saw illustrated here. So that makes this not just an arbitrary table of 16 numbers, but something, well, something problematic, perhaps near paradox. So, what's our argument? Well, we may as well be a little bit more general. So suppose we have sort of sets of possible outcomes, which we can describe just by propositional formulas. I can't completely escape from logic by nature, but it's just formulas that describe different different values that can be assigned to the variables. And moreover, we can assign a probability to each of these formulas, and we're not placing any restrictions on which probabilities can be assigned to which formulas. And the story behind this is that each formula contains some variables, some Boolean variables, which can have possible values 0 or 1, we can just perform lots of experiments where we test for the values of these variables, and then some of those values will satisfy the formula and some won't, and so we get this probability by experiment as the limiting relative frequency. And now we make one assumption of a logical nature, and notice here some element of inconsistency creeps in. Well, some element of the fact that not everything fits together. We just make the single assumption that these formulas are not simultaneously satisfiable. That is, there's no way of setting values 0 or 1 to all the variables, which makes all the formulas true. Okay? Then that tells us that if we take the conjunction of there are n of these formulas, if we take the conjunction of any n minus 1 of them, then whenever those are true, the last one must be false. That's just what saying that they can't all be true is telling us. So that's a little bit of logical structure that we're assuming about these formulas. There's enough of a logical twist there that we can't make all of them true at the same time. Now, equivalently to this, by contraposition, if the nth one is true, then one of the others must be false. Just another way of saying they can't all be set true at the same time. Okay, everyone happy with that? So now we can make a little use of elementary probability theory and reason as follows. From this implication, since probability is monotone, the probability of a smaller set is less than or equal to the probability of a larger set. The probability of the nth formula must be less than or equal to the probability of this union, and this is certainly less than or equal to the sum of the probabilities. That's a very weak property of measures. We're not even invoking inclusion, exclusion, or anything like that. So we have this sum of the probabilities here, but these are probabilities of negated formulas, so that's just the 1 minus the probability of the formula of the ith formula. And now we just rearrange, we collect the terms, and what we get is that under this sole assumption that the formulas are not simultaneously satisfiable, the sum of their probabilities is bounded by n minus 1. Okay? And we've used nothing more than basic logic and probability. So is everyone happy with that argument? If you have any objections, register them now, because we're now going to use them to show that that we are somehow near the borders of paradox, as we were saying. Okay, so this is an inequality that we've derived. Let's immediately apply it to our table. So here is our table again, and what I've done on each row is to highlight some entries on the table. And for each of these entries, I can write a formula which corresponds to the highlighted entries. So, for example, in the first row, I'm looking at the correlated entries, those where the variables both get 0 or both get 1, and this is just the logical formula A1 if and only if B1. So either both are true or both are false. That's what the logical formula A if and only if B says. Exactly the same for the second row, exactly the same for the third row, and in the fourth row, I have the I have the anti-correlation statement, which is just the exclusive OR. This is true when either one of them is true, and when either the first is true and the second is false, or when the first is false and the second is true. It's true just when they have opposite truth values, and logically this is just the exclusive OR of the two variables. Okay, so we have four formulas, just as we were describing in our general setup. And now the second point is that these formulas cannot all be simultaneously satisfied. So how can we see this? Well, for example, if I start with A2, I could use this to say it's the same as B1. I can use this to say that that's the same as A1. And I can use this to say that A1 is the same as B2. And so I end up with B2 exclusive OR B2, which can never be true, because an exclusive OR is only true when the two arguments have opposite values. And if it's the same variable, that can never happen. So does everyone agree with me? These formulas cannot be simultaneously satisfied. Okay, well in that case, we can apply our derivation from the previous slide to conclude that the sum of the probabilities of these formulas must be less than or equal to 3, right? We have four formulas, they're not simultaneously satisfiable, so their probabilities must be less than or equal to 3, because that was the only assumption that we made. But now we can just count. And we see that on the first line, the sum of the probability of that event is 1. On the second line, 6/8. On the third line, 6/8. On the fourth line, 6/8. And therefore we get 3 1/4, and we violated our inequality by a quarter. So I told you had to complain before, but there's, so there is, of course, an assumption. And the assumption is, if you think of the Escher painting, the assumption was there was a real building of which we saw all those snapshots. And the assumption we're going to have to abandon is that there's a well-defined joint probability distribution on all the variables, which gives rise to these local windows we can observe by just measuring some of them. That's the assumption that we're going to have to abandon, and this violation of the inequality is a sort of proving that. So we call this a logical Bell inequality. We have actually just proved a basic version of Bell's theorem. So we can all now prove Bell's theorem, let alone knowing what it says. It's saying exactly that there is no classical source that can account for the data that we had in that table. Now, you might think that this was just telling us, well, this was a sort of science fiction story about Alice and Bob, and the table that we gave down could not reflect any possible experience that Alice and Bob could actually have. But we can now say, in a very empirically well-grounded sense, that this is not the case. So people have been trying, Bell's theorem was in the 1960s, and experimental tests started in the 1980s exactly to see if these violations would occur. And there were various loopholes and sort of technical issues with these experiments. And the first widely accepted loophole-free Bell tests happened in 2015, just 3 years ago. So here's a Nature letter of the first one that was performed, first published one that was performed in Delft, and there were actually 2 other groups who published also in 2015 with their experiments. And this is, by the way, a picture of John Bell, of Bell's theorem. So it's indeed been a notable event that after a long cycle of work and discussion that these what are generally accepted as rather convincing experimental demonstrations have been performed. And this is a review article by Alan Asper, who led the first experimental tests of Bell's theorem in the 1980s and reviewing these things. And essentially the picture is we have our Alice and Bob, our A and B, you see them here performing their measurements. And what we're doing now is we're introducing not a classical source but a quantum source which creates an entangled pair of particles which is sent to Alice and Bob. And even though Alice and Bob are quite far apart, sufficient spatial separation is one of the technical conditions that had to be fulfilled. Nevertheless, we get the entanglement persists in such a way that we get exactly, essentially, the kind of table of data that we were just describing. So what we described is actually exactly what's being checked in these experiments. Okay, so here's a timeline. Von Neumann gave what are still used as the sort of standard mathematical foundations of quantum mechanics around 1930. There was the famous EPR paradox, which was the first time that the issues of non-locality and entanglement were identified as disturbing implications of quantum theory. And you see the word paradox is used right there. There was a classic debate between Einstein and Bohr, which at the time Bohr won, which kind of closed off most discussion of the topic. But it was Bell who came back to it and proved this remarkable result. Essentially, no classical source can explain something predicted by quantum mechanics in 1964. First experimental test by Asper and his colleagues in the 80s, and then the developments of quantum key distribution, quantum computing, quantum teleportation, Shor's algorithm, and these first loophole-free Bell tests just 3 years ago. Okay, so I don't want to go into details, but the thing that's the sort of quantum representation of information that lies behind these new possibilities, we replace bits by qubits. So qubits are complex unit vectors in 2 dimensions. They can be visualized as points on a sphere. Because they're normalized, you can describe them with 3 real coordinates as lying on the surface of a sphere. We can measure quantities like spin. Spin is a real thing. Going back to the Stern-Gerlach experiment, a new phenomenon which illustrates quantization, the fact that from apparently continuous variables we only get sort of discrete outcomes in a fairly dramatic way. So we deflect some beam of particles by a magnetic beam, and then they hit some plate, and rather than smearing continuously on the plate, so if they were little spinning tops, they could go at any angle and be deflected. But actually, up to experimental observation, of course, imprecisions, they essentially end up in one of 2 positions, corresponding to spin up and spin down. And this shows how an informatic quantity, something like a bit, can be represented in a physical system. So the mathematics of it is with complex vector spaces, and things really get interesting when we go to more than 1 qubit, and in particular the phenomenon of entanglement emerges. So here is a state that can be used exactly in the kind of experiment we were just mentioning, a Bell state, as it's usually called, where we have this sort of, because technically we represent compound systems not by a Cartesian product, but by a tensor product, we have this superposition of pairings of states of the individual systems, and some of these coefficients can go to 0, and that can encode high degrees of correlation between what's happening in the 2 parts of the system. So we can no longer say there's really 2 separate particles, each of which has its own true properties. You have to consider them together, essentially. So if you think about this system here, here's Alice and here's Bob. Alice holds her part of the system, Bob holds his part of the system. If Alice measures her part, she may get spin up or spin down, but if she gets spin up, then we say that the state collapses now to one in which if Bob measures, he will only see spin up, and similarly if Alice gets spin down. So this is what Einstein famously referred to as spooky action at a distance. Okay, so this is the idea of how we can use these quantum resources to get these highly non-classical effects. So now let's go to a different way of portraying these we've been talking till now of probabilities, but in fact there's a beautiful qualitative structure which brings us closer to logic and which in many ways captures the essence of what's going on here in this, these contextual phenomena. So we're going to take another example here, similar to the Bell example, but which allows this qualitative description, and this is what's commonly known as the Hardy paradox. So again, notice the word paradox. So we have the same kind of setup. Alice and Bob each have their measurements, A or A prime for Alice, B or B prime for Bob. The outcomes are 0 or 1. But now instead of putting probabilities in the table, we merely put tick or cross, yes or no, depending on whether the event could occur or could not occur. So the distinction is, if you like, probability 0, that's a cross. Probability greater than 0 is a tick. It's possible, without even going into the numbers. And the idea is we can actually realize phenomena which occur as non-classical, as exemplifying this contextuality, even without considering the detailed structure of probabilities, just looking at possibilities, which essentially takes us into the realm of logic. And in fact, I'm going to give a sort of topological or geometric depiction of this very model in this way, as a kind of bundle in the geometric sense. So we have firstly a base, which is the variables that we're measuring. So it's A, B, A prime, B prime. And we draw an edge between two measurements if they can be performed together. So therefore, there's an edge between any measurement by Alice and any measurement by Bob. But there's no edge between two different measurements by Alice. Just if you remember our scenario before, Alice can choose one of the two registers, but she can't look at both of them at the same time. So we have this base, and then above each base we have the fibers, which correspond to the possible values we can see when we do measure these variables. And then we're going to put edges between elements of the fibers if those outcomes can happen together. If we can possibly observe that joint outcome for those variables. So you see in the first row, anything is possible. So we put all the possible edges in these fibers. On the other hand, in this row, we have three possibilities, and one thing that's impossible has probability 0, so we have three edges. One is missing because of the impossibility. Similarly for the second row and the third row. So now we have this structure, which is a kind of discrete fiber bundle, if you like, but it allows us to actually see the contextuality that occurs here. So what should we look for? We can say that a global description, a globally consistent description of these phenomena that would correspond to observations by Alice and Bob of this kind should be a way of assigning values to all the variables which is consistent with what's possible. And we see that in this model there is one way of doing that which is possible. That is, geometrically is just a closed loop that always stays within this bundle, within the possible observations in the bundle. So that can happen. But now, suppose we start with this local observation, the one that comes from here, this edge. Can we turn that into a closed loop that will have a single consistent value for every variable in the system? And in fact, we can continue the path, so we can always continue the path, and that's actually comes from the idea of local consistency. But by the time we get here, you see, we can never come back to where we started. The only way we can continue the path does not bring us back where we started, and we don't have this global consistent description of all the values. And even if we try going the other way, well, the same thing's going to happen to us, that we're not going to come back where we started. So this is what's known as what we call logical contextuality, and this is really what Hardy's paradox is about. So it's a quasi-paradox in the sense that it's again showing we have a family of locally consistent data which can't all be pieced together in a globally consistent fashion. And for an even more dramatic picture of this, we have actually a stronger version of contextuality, and this is a very famous construction in quantum information known as the Popescu-Rorlich box, which actually goes beyond quantum mechanics. But you see, geometrically, it's exactly, viewed in this way, it's exactly a kind of discrete Möbius strip. And wherever you start, if you go around the path, you never come back to where you started, right? So you always come back. I mean, if you start on the top and you go round, then you never come back to where you started, regardless of which starting point you choose. So there's a sort of double cover phenomenon. So this gives us a rather nice and direct visual way of seeing contextuality, which means we're not very far from those Escher pictures we were looking at earlier. And there's certainly also connections with traditional topics in paradoxes as studied in logic. So, of course, there's the famous liar paradox. So the sentence that says, this sentence or I am false. But people also study chains of liar sentences. So chains of sentences where the first one says the second is true and so on, but eventually the n-1 says the nth is true, the nth says that the first is false. So we get this wraparound where eventually there's a twist. And what we can see is that, in fact, the liar circle of length 4 corresponds exactly to the Popescu-Rorlich box. That's exactly what it is. So we're seeing a realization in systems that have been considered in physics of these paradoxical logical structures. And I should say that although the Popescu-Rorlich box itself lies beyond quantum theory, similar phenomena can be found within quantum theory. They just need a couple of extra dimensions, so they're harder to draw. And in fact, the usual reasoning to derive a contradiction from the liar cycle, which you might write by deriving formulas in logic in the traditional way, correspond exactly to going around this path and finding that you haven't come back to where you started from. So the geometrical or topological structure exactly captures the usual logical structure of the paradoxical argument. And so this is illustrative of a much wider class of examples. Okay, how much time do I have left, Marcelo? 10 more. Okay, wonderful. All right, so I thought I would, in fact, illustrate that these very structures that we've looked at, which come out of the heart of some of the major developments in quantum information, actually have more mundane realizations, even in classical computer science. Contextuality is quite a broad phenomenon, this idea of families of data which are locally consistent but globally inconsistent is actually a broad phenomenon that arises in many situations. And one advantage of developing a sort of mathematical theory of contextuality is that one can recognize those situations and transfer ideas and results between them. So I thought I'd take what may seem a very mundane topic by comparison with quantum mechanics, namely relational databases. So like them or love them, we all have a lot of data of important to us on relational databases. And these are just tables, but actually they're remarkably close to particularly if we take the qualitative view, although one can also look at probabilistic databases. But if you take the qualitative view of contextuality, you see that the phenomena directly apply to the database world. So I guess we've all seen these kind of tables. So you have a data table where you have a number of attributes or fields, and then you have entries for tuples which populate the table. And then a query is sort of asking questions about these tables, which again is incidentally a major application area for logic in computer science. Anyway, so let's look at that Hardy model, which we illustrated as a bundle a moment ago, just by looking at possibilities, so ones and zeros. And in fact, by just a small change of point of view, we can turn it into a little relational database. So the point of view is that we now think of the measurements. I mean, they started off as bit registers, and they turned into measurement settings, and now we're thinking of them as the database attributes or field names. We think of the outcomes or the measured values as the data values that can occur in the tuples, and a joint outcome of a measurement in a table is a tuple, as traditionally discussed in databases. So if we do that, we turn our table with 4 rows into 4 little tables which populate a relational database. So there's a different one for each set of attributes corresponding to the measurement settings. So this is essentially an isomorphism between the kind of tables we've been talking about, certainly at the level of possibilities, and the relational database world. So given that, we have to ask ourselves, what is the property of databases that corresponds to this contextuality phenomenon that we've been discussing in the realm of quantum theory? I mean, it just has to make sense, right, if they're actually isomorphic. And in fact, it turns out that this is a very well-studied property going back to the early days of relational databases and the so-called idea of the whether there is or should be a universal relation. And this was hotly debated in the database world around 1980, whether it should be required that any sensible database should have a universal relation. And what is a universal relation? It's a big table up in the sky with one attribute for every attribute that occurs in any table anywhere of the database, and such that it projects. If you just project by picking out the attributes for a particular table, it projects to give you exactly that table in the database. And if you think about it, that projection corresponds on the qualitative level, what with probabilities we talk about as marginalization and so forth, and that is the universal relation postulate. Incidentally, there were these database wars around in the late 70s, early 80s. The conclusion, interestingly, was that the universal relation condition or requirement was too costly for databases. So almost certainly the databases out there on which our data is recorded do have instances of contextuality lurking. So that's an interesting thought. Hopefully it won't affect our medical records or pensions. And we can make quite a comprehensive dictionary between the world of relational databases and these kind of observational scenarios we've been discussing in the context of quantum contextuality. And also with the sort of geometric view that we were mentioning of them. And this goes quite deep. For example, an important notion in database theory is acyclicity, which is a fundamental condition for good behavior of databases, and this actually corresponds to a meaningful condition in the world of probabilistic models of data, which guarantees that you always have non-contextual descriptions. And actually, there's a deep theorem originally proved in game theory, which, due to Vorobyev from about 1960, actually before Bell's theorem, which proves that. Not proving the same result as Bell's theorem, but it's giving general conditions on the sort of shape of the structure of measurements that we have, which guarantee that there are always non-contextual explanations, and his conditions turn out to be exactly corresponding to this important database condition. Okay, so this leads to a sort of idea that the mathematics of contextuality is quite general, so we come back to semantics, albeit in a slightly different form. We can think of contextual semantics where these structures arise, and we can find them in many different places. And hopefully the kind of theory that's being developed in depth in the quantum realm and illustrated by the work that's being presented at the session here on mathematics of contextuality will find many applications in the quantum realm, but also maybe beyond. So there's a lot of work that's been done over the last few years by the community in this area. Okay, well, so I'll just very briefly mention some of the people I've had the pleasure of working with on these topics over the years, including Lucian Hardy of the Hardy Paradox, Adam Brandenberger, Shane Mansfield is here, and many others. So, I'll thank you very much for your attention, and happy to speak about these topics while I'm here, and I'm here till Saturday, so thanks very much.
Questions? Everyone's shy. Okay, let me break the ice. Can you go a little bit more on the topological aspects and try to make a flavor of how this twist essentially come back? Now they are used to the pictures. If you come back to your slides with the diagrams, please, they probably understand.
The PR box diagram, or yeah, sure. Yeah, so I mean what it's really saying is that geometry meets logic at this point, because the Möbius style twist that we see in this diagram is exactly what we saw in the actually in the Bell theorem argument, because in the Bell theorem argument when we applied our probabilistic argument, it was actually based on the fact that I'm going to have to go way back, I guess. It was based on the fact that we were looking. There's a lot of these. If you look at the highlighted areas there, they're exactly the things that that would generate those vertices that we have exactly the structure we have in the PR box. So the logical twist was there, but it wasn't, it was sort of weighted by probabilities. But underneath there was a logical structure there, and that's exactly what we were exploiting by showing that these propositions couldn't be simultaneously satisfied. So it was really an instance of this liar-like paradox. And then we could use this inequality that we derived that relates to the probabilities. And I should say that we call these logical Bell inequalities, and this comes from a paper with Lucian Hardy. What we actually showed is that all Bell inequalities arise in this fashion. There's you have to take not just the sort of whether they're inconsistent, but what's the maximum number that can be consistent. But once you do that, then actually all rational Bell inequalities are instances of this logical kind of argument. So that whole method is there. And as we know, that is still an incredibly rich and powerful method in quantum information. It's a mainstay of the whole field, which is used over and over again. A lot of the things we were hearing in the session today, things that relate to shallow circuits eventually come back to Bell inequalities, communication complexity, and all sorts of things. It always comes back to this method, which is even, one can say, as much as the theorem of Bell has been so important for quantum information, but actually at its heart is really a logical structure. So that's one message I would definitely like to convey. So thanks for the question.
Professor, good morning.
Yeah,
Congratulations for your lecture.
Yes, there you are.
I have one question.
Yes.
Yesterday, we had some lectures about doctor scientific initiation. The doctoral thesis is similar with your project work. The
So
doctoral thesis.
I didn't quite catch the...
I think he wants to know about your original PhD thesis. He's searching for advising in how to have a career in science. So, what? Oh, okay. No, his question is different, and is a tough question in the sense that you were not there to see the prize of the best thesis, the best PhD thesis of yesterday.
All right, yes.
And I have to leave, but what I remember, so who can help me on this? Yesterday we started with...
So was the thesis on a related topic?
Okay, yes. They have coloring on graphs.
Yes.
And based on a game.
Yes.
The game approach for coloring graphs. And
yes.
So he's trying to see if your bundles are related to graphs.
Right.
And to
I didn't. Unfortunately, I didn't hear the presentation yesterday. But it might be that it's more related to the talk that I didn't give, because that was very much about games you can play between graphs, and also about homomorphism. So colorings of graphs can be described in terms of homomorphisms from the graph into a complete graph. So an n coloring is the same thing as a homomorphism into a complete graph on n vertices. So there are very interesting things in relation to that. In particular, you can consider the question of quantum advantage for graph homomorphisms. So by using quantum resources, can you get quantum colorings where you can't get classical colorings? And people have studied the quantum chromatic number, and in general the quantum chromatic number is less than the classical chromatic number, because you can translate it into a game, which classically you can win this game, sort of to color with n colors, just if there is n coloring in the usual sense. But with quantum resources, using the kind of strange stuff we were discussing, you can sometimes win it with a smaller number, so therefore you get a lower value of the quantum chromatic number. One of the things of great current interest is to understand the relation between the two, and when you do get this quantum advantage, there's quite an active community of people looking at this kind of question. So maybe that sort of addresses your question. Thank you.
Any more questions? So let me try the last one. You included some other applications of contextuality to biology, social science. Could you comment a little bit on them?
Yes. I mean, there is an area of quantum biology which I frankly know essentially nothing about. There have been applications in areas like linguistics and psychology. I know a bit about those. I think they mostly draw on analogy, and it's actually, in a sense, it's similar to what I was saying with if you have the sort of mathematics of quantum theory is quite rich and takes us beyond the classical sort of common sense situations. So we have a kind of non-classical probability theory, and we have this way of using contextual data. So it can be applied in other areas, and there are interesting attempts to do this in certainly in psychology and linguistics, to name two. So I think it's and I think there's interesting things coming out of those, but maybe it's a bit early to make conclusions about that.
Great. Thank you, Professor. Your last chance to make public questions to him, but not your last chance to make questions to him. As he said, he will be here up until Saturday. Enjoy him. And talking about enjoying, remember that we resume at 2 p.m. here with semi-plenary talks. So there will be one here, another in the twin auditory that's called Auditory 1, just in the other corridor. And remember, we have a party this evening. So everyone interested in the part that has not registered yet, 65 reais, and food and drink are guaranteed up until 10 p.m. And I believe the problem about vegetarian is already solved, but I only believe. I was checking things here, and for this I apologize for being at the same time a chair and checking, but this is the life of organizer and chair at the same time. So let us thank Professor Samson Abramsky again.